NASA plans to have 2 Starlink mini laser terminals on Orion for Artemis III. NASA says their destination is a network with more than 25,000 operating lasers in orbit. The lasers in question belong to SpaceX's Starlink constellation. It sounds like they may have a hardware lead, but rivals can build fast lasers. What they cannot copy at launch is the moving network around them: satellites, routes, handovers, ground stations, and operating experience. SpaceX's potential technological moat is operational path diversity. That means the useful routes available as the network moves or a link fails. To understand the network in depth, we will follow one ordinary internet request through the moving network, build a public scorecard for moat strength, and then ask whether outside spacecraft are really beginning to depend on Starlink. Finally, we will give Amazon, Kepler, and other launch ecosystems a fair path to compete. If you like evidence-first explanations of space systems, subscribe to Galaxial Frontiers, like this video, and join the community on YouTube or Patreon. Imagine you search the internet through a Starlink terminal. Your request is broken into packets and sent by radio to a satellite overhead. If the best route back to Earth is somewhere else, the satellite can pass that packet by laser to another satellite. The choice depends on satellite position, open links, and traffic. Satellites race around Earth. Each laser has to find another fast-moving satellite and keep its beam locked on the target. As they move, a connection may hand over, a route may shift, or a blocked path may disappear. Eventually, the packet reaches a ground gateway and an internet entry point, where Starlink connects to fiber and the wider internet at large. The satellites and ground sites form the network. The links between them are the routes your data can take. What matters is not how many routes look possible in a diagram, it's how many still work as satellites move, connections drop, and traffic shifts. That gives us a way to estimate moat strength without seeing behind the curtain in SpaceX's control room. The score includes 5 key things: the quantity of satellites with working optical links, coverage across different orbits, ground gateways and internet entry points, non-SpaceX spacecraft that have Starlink-compatible hardware, and resiliency evidence that shows how the network can reroute traffic when a link fails. NASA's figure of more than 25,000 operating lasers is useful, but it tells us neither the number of satellites nor how many routes are available at once. One independent study mapped 33 internet entry points and 70 backbone connections on the ground. That reveals part of Starlink's ground network, but not the laser network in space. Public data can show how many routing options Starlink might have. It cannot tell us how busy those routes are, how often they fail, or whether customers get better service. The Moat score is really just an estimate, but not a final grade. Now compare Starlink's dense moving network with a newer network that has far fewer satellites. More active satellites can mean more relays, more handover choices, and more ways around a failure. Independent research describes Starlink as a mixed network that is constantly changing, not the fixed grid shown in marketing materials. Other studies show the trade-offs between how quickly a laser connection forms, how often routes change, and the delay or instability users experience. These studies do not measure Starlink's production network, but they explain why one fast connection is just not enough. A route that lasts 10 seconds, takes too long to connect, crosses a congested satellite, or ends far from a useful ground station may add little value. Scale helps only when operations turn potential connections into reliable links. So why might that advantage last after competitors launch more satellites of their own? Because SpaceX controls far more than just the lasers. It builds the satellites and terminals, launches them, and operates the gateways and ground network. That creates a tighter feedback loop. If a component fails in orbit, that lesson can be built into the next satellite. A coverage gap can change the next deployment. A routing problem can become a software update, a ground network change, or a replacement launch. That is the deeper first mover advantage. SpaceX is not simply just early, it is already running the system that tells it what to improve next. Now, we cannot publicly measure how effective that feedback loop is, but rivals still have to coordinate the same efforts, either inside one company or across several suppliers. More launch competition could make orbit cheaper to reach without instantly creating working laser links, grounding experience, ground connections, or customers. A rocket can put satellites in orbit, but all of these pieces alone do not instantly turn them into a mature communication network. This is where Orion's 2 terminals become more important than the headline number. NASA is not planning to recreate a global relay constellation for just one mission. It plans to place 2 mini terminals on Orion and connect with mature infrastructure already in orbit. Muon Space says its Halo spacecraft will integrate Starlink mini laser terminals, targeting up to 25 gigabits per second across distances up to 4,000 kilometers. Those are company targets, not results independently measured in service. Starcloud has also reportedly purchased more than 50 Starlink laser terminals for proposed orbital data center network. None of that is the same as a demonstrated service. Together, though, these examples show outside companies actually designing spacecraft to connect with the Starlink network. That can start a flywheel. More compatible spacecraft create more demand, which can support more coverage and ground connections, so on and so forth. Also, it can raise switching cost. But all of this only happens if the service works, the interfaces remain available, and customers accept dependence on a single proprietary network. These announcements show the direction of travel. They do not guarantee Starlink is going to become the gold standard. Let's talk competitors now. Amazon has demonstrated a prototype optical network. Its July 2nd, 2026 status was reportedly 396 satellites launched across 14 missions. That is some real progress, but launches do not prove that laser links are working or that relay service is comparable. Kepler says it has launched 33 satellites in the first group of an optical data relay network designed around Space Development Agency compatible links. Its strategy may appeal to customers who value open interfaces or government interoperability. Other competitors could specialize in polar coverage, sovereign control, guaranteed service, or routes that Starlink does not prioritize. Furthermore, new launch providers can also reduce dependence on SpaceX for deployment. We still do not have public side-by-side service data showing that Starlink routes traffic better than its rivals. So the real test is simpler. Which network stays connected long enough, hands traffic over reliably, reaches the right ground station, and recovers when a link fails. A rival does not have to match 25,000 laser links if it can win that test. This is the strongest case against the Moat. Quantity is not quality. A laser can be installed but unavailable. Geometry can block a link. Pointing and acquisition can take time. Ingestion can funnel many possible routes through the same bottleneck. Policy can prevent an otherwise valid hop. A software fault or common hardware defect can affect many satellites at once. And most traffic still depends on ground gateways, fiber, peering, spectrum, and permission to operate. Maintaining a large fleet is also expensive. A smaller network could beat a larger one on a selected corridor, a demanding service guarantee, or an interface customers trust more. Governments may prefer sovereign infrastructure. Spacecraft builders may resist lock-in. Regulators could push interoperability. The Moat weakens if rivals deliver similar reliability with fewer satellites, if terminals can switch networks, or if Starlink's extra scale barely improves recovery or delay. Those are the tests that will decide whether this moat is real. Operational path diversity matters only when the routes are available, affordable, permitted, and good enough for the customer. So does SpaceX have a network moat with Starlink? Based on the evidence we can actually see, I'd put Starlink's network moat at about a 7 out of 10. Their infrastructure lead is formidable, but until we have better evidence on reliability, recovery, and sustained outside adoption, calling it unassailable would be a step too far. Currently, their advantage is not one uniquely fast laser. It is a working network with more ways to hand traffic over, routes around failure, reach the right ground station, and learn from experience. SpaceX also controls the satellites, terminals, launches, gateways, and customer relationships around that network. Competitors can still break the advantage with better service, open standards, specialized coverage, or terminals that switch between networks. But as Starlink keeps operating and third-party missions choose to connect, the full system could become harder to reproduce. That brings us back to Orion. NASA plans 2 small Starlink terminals because the relay network is already in orbit. Each useful route makes that network more valuable. Each mission designed around it makes the network harder to replace. If the cycle continues, Starlink's 25,000 lasers may become more than a head start. They may become the network the rest of the space industry builds on top of. Thanks for watching, and I look forward to seeing you in the next Galaxial Frontiers video.